In this unit, we have discussed gravitational potential energy because gravity is so common, so it makes sense in our everyday lives. We encounter that quite frequently. So we did that analysis, but now we're ready to also consider spring potential energy because it too is pretty common. Stretching or compressing springs or any other elastic band like a bungee cord. You know, if you ever do bungee jumping, I'm sure you'll be doing that quite frequently, so this will apply to that. I'm sure you're glad to know that. In our analysis of springs previously, we looked at the relationship between applied force and the stretch, and what we discovered was a nice simple relationship, a straight line to the origin. Now the slope of this line would just be the applied force over x, F over x, and that's the proportionality constant relating force and x. We're going to call that K. K is the spring constant. The spring force itself then, well, it's Kx, that's the magnitude, because if we take the x and multiply it by the slope, we get the value of the y value, namely the applied force. So Kx is that force. But being a little more careful, F spring is minus Kx. Why? Because when we stretch, say I stretch a spring to the right, what is the direction of the spring force? Well, the spring force goes to the left. I can't show an arrow there real easy, but in any case, it's going to the left when we stretch it to the right. The spring will pull or push in the opposite direction that you, as an external agent, force it. If you push on the spring to compress it, it'll push back on you the other way. If you pull on the spring to stretch it, it pulls back on you the other way. So there you go. That's what the minus sign is for. Now, what average force would replace this, uniformly increasing force? Well, since it's changing uniformly, the midpoint is the average. So there it is. Basically, the area under both graphs here, under the blue and under the red, are both the same. This triangle is external to the red one. This triangle is external to the blue line. So anyway, they cancel out. So F average is this value plus this value, and then divided by 2. That's what that is. So that's just 1/2 Kx. Now the work done by the applied force. We're going to stretch the spring. That's the force that arises from that. It's going to be that average force times x. So just the area under here. That average force we just discovered is 1/2 Kx. And then if we stretch it x, the 1/2 Kx gets x multiplied by it, and we get 1/2 Kx squared. That is the work done by the applied force in stretching the spring. So this is the work done on the spring. And when we do that work on the spring, it increases something. We're storing that work as potential energy, spring potential energy. By how much? By the amount of work that we did, which is 1/2 Kx squared. It's the work that we do that converts into potential energy. Just like pushing an object up through a gravitational field increases the gravitational potential energy by mgh. Same difference here. So subsequently, the spring force. Now that the spring is stretched, it wants to pull back, and it can do work on something, an external object, of the same amount of work that was done to it in the first place. So the spring force on an external object will trace the same path, force versus distance, or stretch, that it took to stretch it in the first place. So it can perform work on an object equal to the work done by the applied force to stretch or compress it a distance x. So the work is stored in potential form. It's sitting there waiting. It's got a stretched, it's got a non-equilibrium. Well, it is an equilibrium if you hold it stretch, but that's not where it wants to be. It's sitting there patiently waiting to spring back and do work on something, and so it's potential. And it's a conservative force. So here is the formula then for the potential energy. Potential energy actually just ends up equaling the work done by an external force to stretch it, which is 1/2 kx squared. That is spring potential energy. Well, you already are experts on gravitational potential energy. So what I want to do now is put together the conditions when there is only gravitational and spring potential energy taking place. And so we're going to write the energy equation associated with a spring, in this case we have a vertically vibrating spring mass system. So this spring is going to stretch to different amounts. It's like an oscillating subharmonic motion, right? You've encountered that. But also the gravitational potential energy is changing because the heights of the mass m are changing. So let's put them together at the same time. So that's the only forces acting are gravity and spring forces, gravitational and elastic forces. Both are conservative forces. And in conservative forces, you don't lose any energy as heat. So the mechanical energy then is the kinetic plus the gravitational potential plus the spring potential at any time or at any place in its oscillation. This is going to be true. The mechanical energy is a combination of all these three, interchanging between the three of them. Yes. So that's going to be 1/2 mv squared, the kinetic, the gravitational potential, and the spring potential. There we go. So that's quantitatively what those things are. Give it enough information, we can solve for any variable there that we need. Now, an equivalent way to consider this is that, since it's mechanical energy only, the delta K, the delta U sub G, the delta U sub S, all added together will give us 0. At the expense of kinetic, kinetic goes down, one of these will go up, or, there's interchange between all three of them. Well, since they're all 0, we can then consider that the deltas are changes, and it's final minus initial, or position 2 minus position 1, position 2 minus position 1, position 2 minus position 1. So we can put all the ones on one side and all the position 2 energies on the other side and come up with a super duper powerful problem-solving variation of this. Because when you just look at this, it's actually very powerful, but okay, what do we do with that? Well, what I just said, 2 minus 1, 2 minus 1, 2 minus 1, separate the 2's and separate the 1's and put them on different sides. And we get K1 plus UG1 plus US1 is K2 plus UG2 plus US2. And that is great. So pick a place, say right here. The K1 plus UG1 plus US1 is going to be the same as the combination of those things up at a different place. And typically in a problem, you might relate it to a place where it's starting from rest, and maybe there's no U sub S. So UG1 equals all the other stuff at a different point. And that can be really, as I said, very useful.